Hi, I'm Coach Cowland, and in this presentation we're going to look at simple harmonic motion, or SHM. So simple harmonic motion is similar to, but not the same as wave motion or circular motion, and we're going to be going through those afterwards. So some of the variables that we're going to look at, a lot of these will repeat themselves both in simple harmonic motion and in waves and circular motion, though not all of them. Frequency, the period of oscillation, the angular velocity, the length, which is going to be part of the length of a pendulum, the spring constant, the amplitude, that's the amplitude of oscillation, the displacement from its rest position, and the angle. The angle is going to be in radians this time, so that will need to be something that you change on your calculators. So periodic motion, uh, wave motion, circular motion, simple harmonic motion, these are all forms of periodic motion, and periodic motion is a function of motion that repeats itself over regular periods of time. So here you can see this curve repeats itself over a period of time. The x should be a t here, and the p here is the period of time it takes to go from the lowest point back to the lowest point. And if I were to take any point on this curve, say this point here, and I measure the length to the corresponding point on the next wave type thing, you'd see that that is exactly the same. So just to compare simple harmonic motion with circular motion, we're going to look at circular motion. You can see that this is a circle where the motion goes around counterclockwise here. The angular velocity is the velocity at which it goes around and completes its circle. The tangential velocity, you can see changes at each point. It is perpendicular to the radius and tangential to the circumference. And the acceleration is always acting inwards, always acting in towards the center of the circle. So here we have, in comparison, simple harmonic motion, and we can see that the acceleration always acts towards this blue dashed line here. This blue dashed line is the rest position, and the acceleration is always acting in towards it, so it's constantly changing. The definition of simple harmonic motion is a harmonic motion of constant amplitude in which the acceleration is proportional and directly opposite to the displacement of the body from a position of equilibrium. So going back to the graphic, you can see that the acceleration gets greater the further away it is from its rest position, and you can see that the velocity is changing in different places as well. So to calculate the period of oscillation for a simple harmonic motion oscillator, the equations are slightly different depending on what kind of oscillator they are. For a pendulum, the period of oscillation t is equal to 2 pi times the square root of the length of the oscillator divided by the acceleration due to gravity. For a mass on a spring, the period of oscillation t is equal to 2 pi times the square root of m, the mass, divided by the spring constant k. For both of these, the period is inversely proportional to the frequency. The frequency is the number of oscillations in a second, and it's equal to 2 pi over omega, the angular speed. So the displacement of an SHM oscillator, if I want to find out how far the object is from its rest position at any time t, the displacement x is equal to a, the amplitude, times the cosine of omega t. So energy. We know that the kinetic energy is proportional to the velocity squared. So the kinetic energy is going to be dependent on that velocity. And if we look at this simple harmonic motion pendulum, we can see that the velocity is constantly changing. In fact, the velocity is at its greatest when it is at this rest area here. The reason for that is that after that point, the pendulum starts to climb, and as it climbs, it gains gravitational potential energy. As it gains gravitational potential energy, it loses its kinetic energy. At the point where the pendulum is at its maximum height, its velocity is in fact zero. So here we have a vertical spring with a mass on it. There are there are two different types of spring mass questions. There are vertical ones and horizontal ones, and we'll look at both of them. So the energy for this is a little complicated. You can see that all three forms of mechanical energy are involved here. On the right, we can see that the total energy stays constant, and these two dashed lines are the maximum and minimum amplitude of the center of gravity of the mass. And you can see that when the spring is stretched to its maximum, its elastic potential energy reaches a maximum. When it's compressed to its maximum and is vertically at its highest point, the gravitational potential energy is at its maximum. And exactly halfway in between, around about here, is where you will find that the kinetic energy is at its maximum, although it's not as high as the other two. So here we have a horizontal spring. At x equals 0, that's the rest position. At plus x is the maximum amplitude. At minus x is the minimum amplitude. So how do you think that the energy is going to look for this particular simple harmonic motion oscillator? So we can see from here the constant energy is the red line along the top, and you can see that that doesn't change. The kinetic energy is at a maximum at its rest position, just like the pendulum, and the elastic potential energy this time is at a maximum at its maximum displacement, i.e. at its amplitude, both compressed or stretched. So in addition to looking at energy in simple harmonic motion oscillators, we're also going to look at forces. What do you think is going to happen with the forces for this? So here we can see the major force acting on a pendulum is the mass, the weight. And because of that, the force due to gravity is acting with the weight. You can see that the higher up it gets, the greater the force acting to pull it back into its center is. You can also see that it changes direction. The closer it is to its rest position, which is here, the more horizontal the force is, and the closer it is to its amplitude, which is up here, the more vertical it is. And obviously you can also see the change in magnitude of the force. So again, when we're looking at a spring, how do the forces act here? Well, the force here is a restoring force. This is Hooke's law, F equals minus kx. And you can see that the more a spring is displaced from its rest position, the more force is needed to restore it. And Newton's third law says that every action has an equal and opposite reaction. And that means that the more force that is needed to restore it, it also requires more force to stretch it further or compress it further. Okay, thanks for watching.